So in the last video, we talked what QSP was, we did some equilibrium problem solving. We're going to do some more complicated problem solving in this short video. So the next problem I wanted to take a look at was some applications of solubility equilibria. Mostly what that means is I have this really awful titration that somebody from the depths of hell has decided to give to us. And what it says is, I have a saturated solution of barium hydroxide. What that means is I've got the solid in solution and I've also got the ions in solution. So there's some solid like hanging out at the bottom. It's titrated to equivalence by a certain amount of a strong acid. So again, remembering our acid and base rules. This is going to be really important because our base, which is barium hydroxide, is not very strong. Determine the Ksp of the barium hydroxide. Okay, I have two things I need to tackle here. Number one, I have to tackle the fact that I've got a titration. Number two, I've got to tackle the fact that I've got a solubility equilibria going on. Those two things we're going to tackle one at a time. All right. So the question is still written at the top, but I wanted to just kind of walk you through my work. The first thing we have going on here, we need to deal with the fact that we're doing a titration. So what I did was I took all of the numbers from the problem and I wrote them underneath my titration equation. So I've got my barium hydroxide, my two HCl's, so this is going to be a balanced equation, turning out water, so it's a neutralization reaction, and barium chloride. Again, all my numbers are underneath. What I'm looking for here is I am going to start with my HCl. The assumption we're going to make is that, again, we're titrating to the equivalence point. So what you have to remember is at the equivalence point, the moles of H plus equal the moles of OH minus. So while they don't tell me how what the molarity of the barium hydroxide is, I can figure that out because I know the concentrations are going to be equal at the equivalence point. So let's first figure out how many moles of the H plus that we have. So we're going to start with our volume of the HCl. I turned that into liters. I then used the molarity here to turn it into moles. I used my mole ratio to turn that into barium hydroxide. And then what I did is because I have moles on top, I just put volume on the bottom to turn it into molarity of barium hydroxide. That's what I was going for. Okay. Now, once we solve everything, we come down here and we get that the concentration of barium hydroxide is 0.1080 molar. What that means is there was that concentration of barium hydroxide gave me enough OH minus ions to be able to react with the HCl. So I still don't know like what's going on over here. It was a 50 ml sample, still don't really care about that. But I do know that because this is the solubility, this is going to be a single X term. So I take this number and I know that's how much must have dissolved in solution. Now, because I get two hydroxides for that amount, I'm going to have to times that by 2, which is exactly what I did there. On the bottom, I've got my Ksp expression set up. I've got products over reactants, barium 2 plus, OH minus, and that's going to be squared because of our coefficient of 2. We take those numbers, we multiply them together, and we get a Ksp of 5.039 times 10 to the minus 3. And that's going to be our answer for this question. The second question I wanted to do, some of you guys wanted to see this one, is calculating what mass of precipitate forms when you're doing these solubility equilibria. And it's kind of yucky and gross, but this was probably the easiest example I found. I didn't see any in your Zumdahl book. So you're going to have to look on the internet if you really want to find some that have massive precipitate. So what they're doing is they're giving you the molarity and volume of two solutions that are mixed together to form a precipitate. And in this case, our precipitate is going to be calcium plus 2. And then we've also got sulfate, 2 minus. So really what we're making is calcium sulfate, right? That's going to be our precipitate that we're looking for in solution. They also gave us the Ksp of 7.1 times 10 to the minus 5. The first thing I'm going to do, just like before, is ask myself, what reaction is taking place? And in this case, I've got the two ions coming together to form the precipitate. Okay, how many moles of each do I have? Because these are being added separately, I can't be assured that this is going to be an X and this is going to be an X, even though they're 1-to-1 ratio. I don't know that because those solutions I just have in a beaker, and I'm just adding them together. Calculating the numbers of moles of each, what I find is I actually get an equimolar solution of both. This is a really awesome thing because it makes the math much easier. So if we go down a little bit, let's see. So if we go down a little bit, what we'll see is we need to find the limiting reactant. So we've got the calcium, we've got the sulfate. This goes down to 0, and this goes down to 0. Because they're equimolar and they're 1-to-1, they're going to react completely with each other, cranking out 0.0500 moles of my precipitate. The problem with that is this is actually an equilibrium expression. So not all of my calcium sulfate is going to stay undissolved. Some of it, it's slightly soluble, so some of it is going to come out of solution. Start with the number of moles that you had before. Because this is going to shift to the right, we're going to go minus X there, and we're going to have plus X here and plus X here. Our Ksp expression is calcium 2 plus, sulfate 2 minus. They gave us the Ksp, if you remember at the beginning I said what that was, and it's going to be X squared, square root both sides. And this is what you get in terms of moles of ions. So once you get the moles of ions that you have, that is how much of the calcium sulfate breaks apart, okay? So I need to take the initial number of the moles of the calcium sulfate I have, subtract the moles of ions that I made, and this will tell me how many moles are remaining. To find the mass of that, it's just a simple stoichiometry problem at that point. So when we go down here, we're just going to take that number of moles, we're going to turn it into grams, and then we've solved for the mass of precipitate.